The first quiz problem today was to consider a beam with a uniform beam, so its center of mass is at its center. Beam has a length L. Haven't labeled the L here, but we said the center of the mass is at an altitude L over 2, where the altitude is measured with respect to a constraining point here. The beam is constrained to rotate about this point, much as you saw in the preceding video clip. You can think of the meter stick if you wish, so that the beam falls, and when it's at angle theta, it will fall in some distance delta H. Now the first thing we look at is potential energy change. From this we're going to be able to determine the angular velocity of the beam at any point, at any angle, so that the or at least for any delta H. If we know the angle, we can find the delta H fairly easily. So the change of potential energy is negative because, of course, we're descending, and of course we take the mass times gravity times the change in the altitude of the beam. Now that change in altitude, the average change of altitude of the beam is the change of the altitude of the center of mass. So that the delta H here multiplied by the weight of the beam gives us the change of potential energy. Potential energy will be the negative of that product. Now if the beam starts from rest, as we saw, the kinetic energy at any instant will be the negative of the potential energy change, which is going to be just mg times the magnitude of delta H. Now I put magnitude signs around the delta H, absolute value signs, just to alleviate any confusion. In labeling delta H with a double arrow in the original figure, I implicitly said that delta H is a distance, which makes it positive. So the absolute value signs aren't really necessary, but I'm going to keep them there just to avoid any confusion. Well, if the kinetic energy is mg delta H, then the I omega squared for this situation, for this beam, is mg delta H, which means that omega is 2 mg delta H over I, square root, if I didn't say that. The moment of inertia of a beam constrained to rotate about its end is 1/12 ml squared. I'm sorry, 1/3 ml squared. Constrained about the center is 1/12. So that we substitute the 1/3 ml squared for the moment of inertia and simplify the expression, and we see that omega is 6g delta H over L squared. So that the angular velocity can be found as a function of delta H, but of course delta H can be found from the length of the beam and the angle theta. When the beam is at angle theta with respect to horizontal, the center of mass, which is at position L over 2 from the end of the beam, will be at L over 2 sine theta. Simple solution for this side of this triangle. And that's going to be the altitude, H. The delta H is going to be the original altitude, which is L over 2, minus the altitude to which it's fallen here. So that our delta H is L over 2 minus L over 2 sine theta. Factoring out the L over 2, we get L over 2 times 1 minus sine theta. So that we can express omega, which was, you recall, originally 6g delta H over L squared, as, since delta H is L over 2 times 1 minus sine theta, as 6g times L over 2 times 1 minus sine theta over L squared. Which simplifies to this, dividing the L into the L. And it doesn't simplify to this. This 6 needs to be a 3. Because we divide 2 into 6 to get 3. So this should be the square root of 3 times 1 minus sine theta over L. So this is our angular velocity when we're at angle theta. This will apply to the meter stick, the ruler, or any other uniform rod or beam that we drop in this manner.